Hi, class. I'm going to show you those problems we skipped from lesson 4-5 with the U substitution. I call them the double U substitution, but I had you skip like numbers 68 and 70, something like that in your homework. So I'm picking one from the textbook, and then I picked one of your homework problems. I think this one was number 70. And we're just going to go over these two problems, and then I have one last circuit for you to do before I come back to school tomorrow, and we can start chapter 5. Okay, so just like before, you still want to choose U as your inside. This is still kind of undoing chain rule, so if I'm looking at this definite integral here, I would let U be 2x minus 1. And you'll have to bear with me with my handwriting. I'm using my finger on my tablet at home. So, okay. Same thing. We're going to take the derivative with respect to x. So we get 2 from our chosen u. And then we notice, once we do times both sides by dx, we get 2 dx, and you're like, ugh, I have this leftover x up here, and that's not anywhere in my derivative. So what we need to do is we need to do another U substitution. This is why I call it double U substitution, not double U. It's one of my jokes, but double U. So what we're going to do is we're going to take what we let U be, and we're going to solve this for x. Okay, so I'm just going to rewrite it over here. So if I were to solve this for x, oops, don't want to change it. If I were to solve this for x, I would start by adding 1 and then divide everything by 2. And I would get that little expression right there. So what I'm going to do is I'm going to substitute both the du and this little expression in for x. Now, before I do that, I see this 2 in my derivative piece. So just like before, if I have that 2 and I don't see it located within my integrand, I want to divide that off and bring it in front. So that's still going to be part of the process if you do not have that within your integrand. Okay. Now, we do have bounds here, so those also need to be in terms of u. So I'm going to come over here, make my little table, plug them into here. So we started with 5 and 1. So 2 times 5 minus 1, that'll give me an upper bound of 9. 2 times 1 minus 1 will give me a lower bound of 1. Okay, so be really careful with my substitution here so you guys can see this. I'm going to start with changing my bounds to 1 and 9. Now I'm going to bring this 1/2 from my du expression out in front just like before. Okay, I'm going to try to use colors here. So from this, u is 2x minus 1. So within my integrand, in my denominator, I have the square root of u. And then I replaced dx with 1/2 du from this down here. So I'm replacing the dx with du, and I already took care of the 1/2. Oh man. Du. Okay, and then I have that x up there. That was not a part of my derivative, so I'm going to substitute this little equation that I solved x for in terms of u so that everything is in terms of u. So up here, I'm going to use that 1/2 u plus 1/2. Okay, so that's all in my numerator. So I'm going to clean this up a little bit. Because the square root of u is u to the 1/2 power. And then I have 1/2 u plus 1/2 in my numerator. And all of that is du. So before I take the antiderivative of this, or antiderive this, I'm going to break up this fraction here. So I have 1/2 u over u to the 1/2. So subtract the powers there. That would give me 1/2. U to the 1 minus 1/2 would be positive 1/2. And then I have this fraction here, 1/2 divided by u to the 1/2. So that would be 1/2 u to the negative 1/2 du. Okay. Now these both do have a half, so you can either keep it there or you could factor it out with that other 1/2 and make this 1/4. I like to do that because the more like constants I can bring out, the easier it is to find the antiderivatives, but that's just a personal preference. You don't have to. We get the same answer either way. So we get to there. Moved up my user looking a little interesting. Okay, now it's simple, just power rule from here when I take the antiderivative. So I still have that 1/4. So here, add 1 to the power, 3/2, divide by that new power. Same thing with the negative 1/2, add 1 to the power, positive 1/2, divide by the new power. And then I have my bounds of 9 and 1. Before I plug in my bounds, let's clean up this fraction action here. So divided by 3/2 the same as I times it by 2/3. Divided by 1/2 same as times it by 2. Oofda. Oh no. Okay, I'm just trying to fix some of my. Here we go. U to the 1/2. 9 and 1. Fundamental theorem of algebra. Plug in your upper and lower bounds. So we'll do that quickly. Starting with your upper bound. That's supposed to be a 3. That's a 3, people. That's a 3. That's a 2. Okay, so plugging in 9, and then subtracting when we plug in 1. I'm going to do that down here. Okay. So hopefully you've gotten some practice in simplifying this. From here, obviously you just have to number crunch. This is just arithmetic. Take that, minus that, times it by a 4th. I got a final answer of 16/3. 16/3. Oh yeah, that looks good. 16/3. There's our first W substitution. Okay, let's try one more. So again, folks, your way that you're going to detect that this is happening is when you decide what your U is, but you don't see its derivative hidden. So here's another good example. Normally, I'm tempted to look within this cube root, and I'm like, ooh, I want to call U my inside x plus 2, but I have this x squared out here. So then you're like, well, should I call U x squared? But then I have this cube root, but the derivative is located inside. So stick with your gut instinct. We still can do U substitution here with letting U be our inside of x plus 2. So I'm going to come over here. X plus 2. Oh, man. Tablet is not being my friend right now. Come on. X, there we go, plus 2. Okay, we can still take the derivative. Du dx would just be 1. Derivative of 2 is 0, so solving this for du is the same as dx. So what I have at this point, and normally I just like to change everything first, but just to give you a little visual here, I have the cube root of u, and then I can just substitute in du right for dx. But I still have this x squared out here. So I'm like, okay, I can't have this. Don't write this down. I repeat, I cannot have x squared and have an integrand that has x's and u's. That's a big no-no. Get rid of that. So same thing. We're going to use this little equation. We're going to solve it for x. And then we'll do a little double substitution. All right, minus the 2 over. So this solve for x is u minus 2. So what we're going to do, I'm going to move this guy over, is we're going to substitute that in for that x squared. Since x is the same as u minus 2, and it's being squared, now I have my whole integrand in terms of u. Don't forget to change your bounds. Let's do that quickly. So we have 6 and negative 2. So 6 plus 2 is 8. Negative 2 plus 2 is 0. So my new bounds would be 0 and 8. Okie doke. Now, before you find the antiderivative, or you're probably thinking, this does not look any simpler, Miss Hentrich, but before I take the antiderivative, we can simplify this. We can kind of multiply this out. I'll start by doing the u minus 2 squared. That'd be u minus 2 times itself twice. That would give me u squared minus 4u plus 4. And then the cube root of u, I'm going to write as u to the 1/3 power, like we normally do with derivatives and antiderivatives, because then we can use power rule. Now I'm going to distribute this u to the 1/3 through to everything. So I get u, and then here we go, we add the power, so 2 plus 1/3. 2 and 1/3 would be 7/3. Try that again. 7/3. Okay, minus 4 u to the 4/3. 1 plus 1/3 would be 4/3. Plus 4 u to the 1/3 du. Now this doesn't look so bad to antiderive. Okay, here we go. U to the 7/3. Add 1 to the power. That'd be 10/3. Divide by the new power. U to the 4/3. Add 1. That'd be 7/3 to the power. Divide by the new power. Okay, u to the 1/3. Add 1. That'd be 4/3. Divide by the new power. And then our bounds of 8 and 0. I can just feel Jason getting all worked up about how messy this is, and I apologize. It also bothers me. Okay, let's clean this up a little bit. So dividing by 10/3 is the same as 3/10. U to the 10/3. And again, folks, remember with u substitution, this is just always a good reminder. You don't have to plug this back in terms for x as long as you change your bounds. I know some of your textbook problems, they did that where they like resubstituted it back in and then didn't change the bounds, and that's totally fine if you like that method better. However, I just think it's easiest, especially with these double u ones, to get everything in terms of u, and then you don't have to worry about substituting anything else. Okay, now I'm just doing that 4 divided by 7/3 is the same as 12/7. 4 divided by 4/3 is the same as 3. Okay. So all we have to really do here is plug in 8 because obviously everything contains a u. So when I plug in 0, I'm going to get 0. So I'll just quick show my work for that. 3/10, 8 to the 10 thirds, minus 12/7, 8 to the 7 thirds. I used to have a pen that goes with my tablet, but of course I haven't used it in probably over 2 years. And when I went to try it, it would no longer Bluetooth connect with my tablet. So I don't know what happened. Okay, folks, I'm just going to tell you here once you crunch that nice big long number, you get this lovely 1,209 over 28. Yeesh. And remember, that's the area under that curve from -2 to 6. That's what that means. Okay, I have one more circuit for you guys, and we'll take a break from the circuits for a while after this one. But I want to give you a heads up that there are some of these double use substitutions in the circuit. So it's great practice for you to try some on your own. And there's also just normal use substitution mixed in with some Riemann sums. I just got done finishing the circuit. It was actually pretty fun. It was just a good mix review for chapter 4. And like I said, we'll move on to chapter 5, and I'll see you guys tomorrow.